Happy Friday, everyone. Welcome to another exciting episode of our series on RF and cable basics. I'm your host, Brady Volpe, founder of the Volpe firm and Nimble This. And today's topic is all about signal levels, but before we dive in, I want to introduce our special guest, Ron Hranac, a 50-year veteran in the cable industry who has worked for cable operators and vendors during his career. Ron's expertise is unparalleled, having received numerous awards and recognitions throughout his career, including induction into the Society of Cable Telecommunications Engineers (SCTE) Hall of Fame. As we discuss signal levels in today's video, Ron will be sharing his wealth of knowledge and experience on this subject. With his extensive background in the industry, Ron has published countless articles and papers and has been featured speaker at numerous international, national, regional, and local conferences seminars. Be sure to check out his full background in the description below. So whether you're new to the cable industry or a seasoned professional, today's episode is packed with valuable insights that you definitely don't want to miss. So grab your favorite beverage, sit back, and let's dive into this great presentation with Ron Hranac. So let's get on to the show and get started and talk about signal levels. Ron, how are you doing?
Well, happy Friday, Brady. Thanks for the kind words in the introduction. Looking forward to continuing the discussion that has as its foundation the decibel, which we discussed last time we were together. So today's presentation, as you noted, Brady, is about RF signal level and cable networks, and taking the decibel and turning it into a unit that we can use to express signal level. So I'm going to click on the share screen button here if it's time.
Absolutely, Ron. Let's get started. Go ahead, share your screen. I think this is going to be a great follow-up to the what is a decibel from last session here. So your screen is coming up, and we are absolutely ready to get started.
All right, let me move this little deal over to the right here. So the topic is what the title says. What is signal level? And
yes. What is a signal level, Ron?
Well, when measuring signal level at, let's see, at a tap or the input to a modem or the input or output of an amplifier, what is it? What the heck are we measuring? Well, the simple answer is we're measuring the amplitude of that signal. But what's that mean? So I think to understand that, it helps to start with some basics. And of course, keep in mind that it's even more helpful if you saw the presentation that we did last time on this program about the fundamentals of the decibel. So I want you to sit back and think for a moment of a different way to look at a signal from the time domain perspective. Some of you may have experienced using a piece of test equipment called an oscilloscope. This displays a signal or signals as amplitude versus time. A spectrum analyzer that most of us are familiar with displays signals in terms of the amplitude versus frequency. But here we're looking at a sinusoidal signal on an oscilloscope that you can see in the upper right corner of the slide. We see that sinusoidal signal in the time domain. So that horizontal axis is time, the vertical axis is amplitude. And it's an alternating current waveform or an AC waveform. And you think, well, wait a minute, I thought you were talking about RF. And I will tell you right now that RF is based upon AC waveforms, and that'll become a bit more clear here as we go along. So looking at the slide, you can see a graphical representation of a sine wave, and in this case, we can look at that and think about different ways we can characterize that sine wave. We can see the amplitude that's displayed on the left side of that. We can see an individual cycle that's highlighted with the graphic. And then we can see the horizontal axis being labeled time or phase. And as we think about ways to measure an AC source, we can measure the AC signals peak to peak, root mean square, or average values of parameters such as current and voltage. And as you look at the diagram on this slide, you can see the AC signal source over on the left. We can use an ammeter to measure current, and you'll note the ammeter is placed in series with the circuit, and we place a voltmeter across the circuit, in this case in parallel with the load, to measure voltage. And those meters can display all those different ways that I just mentioned: peak to peak, root mean square, or average. You think about, okay, well, I've heard those terms before, but what do they really mean? And as you look at this graphic, this shows the relationship among all those parameters. So you can see peak to peak goes from the very top of the waveform to the bottom of the waveform. Peak is half of the peak to peak value. So you can see that going from, we'll call it the 0 point here in the center, or the horizontal axis. That goes from that center up to the top, or it can go from the center down to the bottom. That would be peak. We can see average is about 0.6366 of the peak value, and the root mean square value is 0.707 of the peak value. So just heard me use go ahead,
I mean, there's a lot there. So, Ron, we always say it's like it's not the voltage that kills you, it's the current. So you just dropped a lot of different ways that we can look at voltage. Why don't we care just about the peak voltage rather than, peak versus these different terms that you're now introducing to us?
Well, they're all important, and I'm going to touch on that because that's a perfect segue to the next point, and that is voltage or current of an alternating current or an AC waveform is usually expressed as a root mean square value. And a good example is you plug a voltmeter into an AC outlet, carefully and safely, of course, in your home, and you'll note that the electricity from a North American AC outlet is a low frequency, and it's typically 60 hertz, sine wave, whose root mean square voltage is about 117 volts. You might wonder, well, why would you express it in terms of root mean square? And the reason is to get equivalent or effective values that correlate with what's going on in the world of direct current or DC. So, for example, 10 millivolts AC has the same heating effect in a load as does 10 millivolts DC, and the root mean square just makes it a whole lot easier to deal with. But if you go back to the idea of the peak-to-peak value, you could take that 117 volt root mean square value that you measure in your AC outlet at home, and you can figure out the peak-to-peak value, and that's a lot larger than what you think there. But what we're concerned with is the root mean square value.
Okay, so by us understanding the difference between peak-to-peak and root mean square actually tells us more about sort of what the actual intensity of the voltage is, rather than, peak-to-peak might be one value, but root mean square is maybe more the true intensity or the true value of that voltage and the impact that it's going to have in the circuit.
Well, they're all true. I think most of us are used to dealing with DC measurements. For example, a 9-volt transistor radio battery, and when I say transistor radio, I'm probably dating myself. But you measure with a voltmeter and you measure 9 volts. And that's it. It's just 9 volts. There is no peak or anything else. It's just 9 volts DC. But if you have a 9-volt AC waveform, what is that? Is it the peak to peak, the root mean square, the average value? By convention, it is the root mean square value, so that we have an equivalent to what we measure if it were DC. And if you connected both sources, a 9-volt RMS AC source to a resistor, or a 9-volt DC source to the same resistor, they would both have the same heating effect in that resistor. And that's the importance of using root mean square.
So we can compare AC to DC much closer now.
Yes, it becomes an equivalent comparison, and I think that's an important point for folks to remember. Are the other parameters important? Of course they are, and there are situations where you may need to measure a peak value or a peak-to-peak value. But in this case, I wanted to point out how root mean square applies, because as you'll see a little bit later on, that's a very important part of signal level. So let's think about an unmodulated RF signal. We call that a CW carrier or a continuous wave carrier. In the world of RF, though, instead of being 60 hertz like the AC outlet on the wall, It's a much higher frequency alternating current waveform. And yes, it is an AC waveform, but it's typically several kilohertz, megahertz, or gigahertz, or even more. But it is a sinusoidal AC waveform, or can be. Of course, it can be a square wave or some other type, but we're talking about sine waves here. So if we think about an RF signal, we can measure an RF signal's amplitude in a bunch of different ways. We can measure its voltage in volts, we can measure current in amperes, and we can measure power in watts. Now think about all those terms for a minute. Imagine, if you will, that your signal level meter measured signal amplitude in voltage, current, or power. And you have a front panel knob that lets you select between those. And as you look at it, you'd say, that's a pretty clunky way to express the amplitude of an RF signal. They're all legitimate values, but they're not real convenient to deal with. And you can see the needle on the meter there is pointed to a value that says it's 1.423 millivolts. Or if you're measuring current, if you could hook your signal level meter up in series with the circuit, you would measure, and this is assuming 75 ohms impedance, 21.132 microamperes. Or if you were measuring it in terms of watts, this would be 33.492 nanowatts. A nanowatt is a billionth of a watt. And you look at these and go, there's no way that would be practical considering all the different signal levels that we deal with in a cable network on a daily basis, from the head end out to input levels to a set-top box in the customer's home.
Yeah, that would be really, really tough to read if you had that on a meter. And I can't even imagine. And we had a quick question come in, Ron. I just wanted to mention. Dennis asked because you mentioned heating, as we had something go through. So Dennis asked, when we say heating effect, is that in watts? So when the voltage goes through a resistor,
yes,
that's going to be current. That's going to be power, right?
If you connect a source to a load, in this case a resistor, that resistor is going to dissipate that. It's going to function as a load and dissipate the power as heat. In fact, what many people may not be aware of is that if you put a 75 ohm terminator on an unused tap spigot or an unused outlet that's a hot outlet in the subscriber premises, what happens to the RF? And we'll assume that the 75 ohm impedance terminator is exactly 75 ohms at all frequencies. So that resistor absorbs all the power. Well, where does it go? It's dissipated as heat by the resistor. Now, of course, it's extremely low level heat. Yes, there is precision equipment that could measure that, but you're not going to notice anything by putting your fingers on that terminator. You won't feel any heat from that, at least from the RF. Because think about the example here. We have no idea what signal level this is here, for instance, in dBmV, but 26 nanowatts, 26 billionths of a watt is not much power. So from a per channel basis, that will be generated that power will be dissipated as heat in that resistor in the terminator, but you're not going to feel it with your fingers. So yes, it is going to be dissipated. I hope that answers that.
Totally does. And I just want to say, Ron, Oli Frank says, hi from Costa Rica. Just want to thank you for sharing all this knowledge and making these topics easier to understand. So thank you, Oli, but thank you, Ron, for providing this great information.
Well, and you're welcome, and thanks for joining us all the way from Costa Rica. Glad you're here. All right, let's look at an example of measuring signal levels in a cable network. And here it's per channel levels, so we're not measuring total power, we're just measuring the signal level of an individual channel or individual carrier. So we'll assume per channel. We'll again assume 75 ohms impedance for the cable network. And if we think about the different signal levels that we can see in a cable network, they're all over the place. For example, the per channel signal level at the output of a line extender might be 0.1 volt or 100 millivolts RMS. Typical tap spigot per channel output might be 0.00708 volt. Yeah, try to measure that on a meter. Or 7.08 millivolt RMS. Input to a TV set or a cable modem or a set-top box might be 0.001 volt or 1 millivolt, root mean square. And again, this is just the level on one channel. And the input to a line extender might be 0.010 volt or 10 millivolts root mean square. Now, this is just a handful of examples in a cable network. And can you imagine all the different places in a cable network where we measure signal level and all the different values in voltage and how cumbersome that would be to express those
It
signal
sure
levels
gets
in
complicated.
voltage?
If you're a technician,
It does.
it's going to get
It does.
really, really complicated out there, really, really fast.
And of course, the question then becomes, is there an easier way?
I hope so. I hope you're going to give us an easier way, Ron.
And there is. And this is where we go back to the last session we did, which was the decibel primer. And the way we can simplify all these complicated numbers is to use the decibel, or dB. And in the case of the signal levels that I just showed as examples, a signal level in millivolts can be expressed in decibels, the world of the dB, as a ratio of that signal level to 1 millivolt across a 75 ohms impedance. And that equals 13.33 nanowatts, or about 13 billionths of a watt. That's our so-called zero reference. This, by definition, is called dBmV, or decibel millivolt. And that is technically a unit of power expressed in terms of voltage. So in the 75 ohms impedance, the power is 13.33 nanowatts, but we express it as 1 millivolt. Or we express it more specifically in dBmV using this formula. So 20 times the base 10 logarithm of the value in millivolts, whatever that is, divided by 1 millivolt. So let's take that 10 millivolts as an example from that list that I put together. That happens to equal 20 dBmV. The way you figure it out is with this formula. So we take 20 times the base 10 logarithm of 10 millivolts divided by 1 millivolt. All right, 10 divided by 1 equals 10. Next, we take the base 10 logarithm of that, and if you use your scientific calculator, the answer is 1. We multiply that by 20, and we get 20 dBmV. So now instead of saying that the signal level is 10 millivolts, we now say it is 20 dBmV.
Shocking. And I think that's something they almost commit to memory, that the 10 log of 10 is 1. Same way that we remember like 10 log of, keep committing that to memory. The same way we kind of memorize these ratios, but that's an important one. Yeah, or just use your
hooray
calculator.
For scientific calculators.
So that's another important fact is
a lot easier.
Brady's math abilities are terrible, so I always have my calculator or my phone with my calculator built into it.
I still have my slide rule from school. It's a student version sitting up on a shelf here in the office, but don't ask me if I remember how to use it. That was
I never
many
learned.
decades ago, but I did keep it. And yes, we used to use that for all kinds of calculations.
We put people on the moon with a slide rule.
Yes, we did. All right, so now let's go back to those 4 examples that I shared earlier. Remember, the line extender output, this is a per channel value, is 100 millivolts, root mean square. And if we convert that to dBmV, and by the way, this when I created the graphics here that show these sine waves, these are actually to scale relative to one another on this one and the next couple slides. So we can see 100 millivolts root mean square translates to 40 dBmV. The tap spigot output, and here again, you can see this is all scaled correctly. 7.08 millivolt RMS equals plus 17 dBmV. So a fairly typical per channel level at the tap spigot. The input to a TV or set-top box, 1 millivolt is 0 dBmV. And then look at that sinusoidal waveform, how small that got compared to these others.
That got small quickly, but what I'm starting to see here is a trend that using dBmV is a lot easier than talking in nanovolts and root mean square and stuff. That was crazy.
Yeah. And then the last one is the per channel input to a line extender, 10 millivolts RMS, and we did the math on that one in the previous example, is plus 20 dBmV. So there they are. So you look at all those, they're all scaled correctly. So you can see the signal level. And now we go back to our meter slide. Remember that one that had all the voltage and current and power on it? Here it is in dBmV. And by the way, all those values that were on that slide, or that are on that slide, equal these values in dBmV. So you can see, oh, it is so much easier. So we got minus 5 dBmV to plus 5 dBmV.
Yeah, so
And
this is what I want to have on my meter, where that's nice, easy to read numbers versus that first slide that you showed us that was so complicated to read.
oh, yeah. And even if you don't show all three values, just pick one, pick voltage or pick power. But it's still cumbersome because we're dealing with really small numbers to begin with. But there are, in many cases, many decimal places involved. And that just gets one of the, let's pull the hair out here. So dBmV is so much easier. It is so much easier. But now let's throw a monkey wrench into things. The 4 examples I showed you were measurements of a CW carrier, no modulation. What happens if that carrier is amplitude modulated? And you look at the graphic down below. This is a time domain representation. So this is how you'd see it on an oscilloscope. And then the question becomes, where?
Yeah, how do I tell what the peak voltage is? Do I look at the peaks? Do I look at the valleys? It's really confusing.
What part of this signal do you measure to measure signal level? Where do you measure? Well, I'm going to answer the question for you.
Outstanding.
One thing or one way we can do this is to measure something called peak envelope power, or PEP. And you think, oh, this sounds like a new term, and my meter doesn't read this. But as you'll find out later, your meter actually does read this, but we'll come to that in a moment. So peak envelope power, by definition, is the average power in watts during one cycle at the crest of the modulation envelope. So let's look at this amplitude modulated waveform, and we can see that the envelope is highlighted by this red line. That shows us the shape of the waveform. That's the envelope. The crest is the respective peaks, or the highest part of the waveform. So what we want to do is measure the average power during one cycle at the crest of the envelope.
So isn't average, when we talk about root mean square and average power, it almost seems like they should be roughly the same thing when we're looking at something like this. Are they, or are they different?
The formula for power is root mean square voltage times root mean square current, and that gives us average power.
Well, that's kind of complicated, Ron.
Well, remember it this way. P equals IE, pi. P equals IE, like apple pie. P is power in watts, I is current, and E is voltage. And if you remember that, just remember that because we're dealing with AC, we're talking about the root mean square value of current times the root mean square value of voltage gives us average power. Now, there is another factor that has to come into play because when you get into the world of alternating current, we get reactance that can get in the way, and then you have to multiply that by a further factor called it's the cosine of theta, which is the phase difference in degrees between the current and between the voltage and the current. I don't want to dig into that today, but we have to take that into account, and things can get complicated. So I'm making the assumption that our impedance is a purely resistive impedance and has no reactance to really complicate things. In the real world, there's reactance, so it can get a little tricky.
And also that our current is constant, because I think that makes this a little bit more complicated, that we're just looking at the voltage here.
The RMS value of current might be constant, but the instantaneous value, no. Right. So we have to hold on a second. I'm live.
Well, I hope so. I brought you something to eat.
I can't eat now. My wife is trying to feed me now, but anyway. So what she doesn't know is we're live talking to people all over the country. And anyway.
Hi guys.
Hello.
All right, so she says hi. Anyway, so let's figure out a way to measure this varying amplitude sinusoidal waveform, and we're going to start with peak envelope voltage, or PEV. So this is for this example. You'll see the same relationship. Remember the peak and peak to peak and whatnot parameters of a sinusoidal waveform. Well, here we're going to talk about peak envelope voltage. So it goes from the center to the highest part of it. So let's assume that it happens to measure 14.14 millivolt. So 14.14 millivolt. We're going to plug that into this formula. PEP, or peak envelope power, equals peak envelope voltage times 0.707. That's to give us the root mean square value. That value is squared, and then we divide by the resistance, or in this case, the 75 ohm impedance of our network or load. So it's 0.01414 volt. Remember, it's 14.14 millivolt. So in voltage, that's 0.1414 volt times 0.707. We square that, and that gives us 0.01. We multiply that gives us 0.01. We square that, we get 0.0001. Divide by 75, and that gives us 0.0000133 watt, or 1.33 microwatts. That's 1.33 times 10 to the minus 6th watt during each cycle at the crest of the modulation envelope. So that power is during those highlighted red cycles on the waveform. So now we have peak envelope power. And okay, what do we do with it? Well, as before, it would be a little bit clunky to express signal levels in a cable network in PEP, at least in watts. And, say something like, all right, the line extender's per channel input signal level is 0.0000133 watt.
Yeah, that'd be exhausting to communicate to a colleague.
Yeah. All right. So we know from that previous definition that PEP is the average power of one cycle during the crest of the modulation envelope. In an analog TV channel's visual carrier, the crest of the modulation envelope occurs during sync pulses. See where this is going?
And what's a sync pulse again, Ron?
Well, in a video waveform in an analog channel, a sync pulse is a waveform shape, if you will, that triggers the TV set to in its scanning of the lines that make up the picture. So if you remember looking at an old analog TV, it's made up of a whole bunch of lines, horizontal lines. There's 525 of them in that picture, and they're actually interlaced. So there's 262 and a half lines that are drawn across the screen. The electron beam shuts off, goes back to the top, and then draws the other 262 and a half lines in between the ones it just drew. And the sync pulse tells the TV set at the end of the line, turn off the beam, go back to the beginning on the other side, and then turn on the beam and start over again. So the sync pulses
go back to the beginning and start all over again. Okay.
Yep, that's what they're used for.
Makes sense. Thank you,
But
Ron.
anyway, those sync pulses represent the maximum carrier power in NTSC analog video. And as the picture carrier or picture content changes, the sync pulses don't. They stay the same.
Right.
So if we assume 75 ohms impedance, that 0.0000133 watt equals 10 millivolts RMS, or 20 dBmV. And here, 20 dBmV is the RMS value of the instantaneous sync peak. A unit of power, 0.0000133 watt PEP, expressed in terms of voltage. So our signal level meters are, when they report dBmV, giving us the peak envelope power of the RF signal, but in terms of dBmV. So let's put this in perspective that might help clarify it a little bit. The signal you see here or what you see here on the left, is an oscilloscope display of a CW carrier from a head-end modulator. There's no audio carrier, it's just a video carrier. So it's just a CW carrier. And in this case, I actually to get this picture, I hooked the oscilloscope up to the output of a modulator. I had the input to the oscilloscope terminated in 75 ohms with a T, so I get the correct values on the display. There's a bit of an optical illusion here. When I did this was years ago, the peak to peak actually did go to the graticule lines here. But when I took the picture, it makes it look like they don't, but they actually do. So in this case, this is an oscilloscope display. So we've got time in the horizontal axis, amplitude in the vertical axis, and the RMS value of this is 100 millivolts, that 40 dBmV. If we apply modulation, and remember, this is NTSC, so we've got 1 volt of baseband video going to the input of the modulator. Note what happens. The sync pulses stay at the same amplitude as the unmodulated carrier. And in this case, the level is still 100 millivolts. And again, this is kind of an optical illusion that it doesn't line up. But that was the function of the camera I was using and so on with the scope. But the RMS value didn't change, and the peak-to-peak value didn't change. The peak-to-peak value is the same with both the CW carrier and the modulated carrier. In analog NTSC, it's amplitude modulation on the visual carrier, but it's called negative AM, or negative amplitude modulation. So the peak-to-peak is the same with modulated and unmodulated, and the RMS value is the same. And if we run those numbers through the math, then what that tells us is that it's 40 dBmV. And when we measure a signal like this modulated signal on the right with a signal level meter, the signal level meter has in it a peak detector circuit that is looking for these sync peaks. And it displays that 100 millivolt RMS value of those sync peaks, but in dBmV. So that's what it is we're measuring when we measure the level of a carrier of an analog NTSC TV channel.
So you were talking about peak to peak here, the peak voltage, but you're saying 100 volt RMS. Are we getting? Yeah. Which is the correct terminology to use?
RMS.
Okay.
All I wanted to show here was that the peak to peak value stays the same with the CW carrier and with modulation applied. Peak to peak value did not change. The RMS value did not change.
Perfect.
And what we're concerned with is the RMS value, because that's the value that we convert to dBmV. But in order to measure that, the signal level meter has to have a peak detector so it knows where these sync peaks are and knows what the value of those sync peaks are signal level wise. And then it spits out that answer in dBmV.
Perfect. Just sort of unrelated, Ron, but Business Bambi said that she's currently reading our P&M paper from the SCTE February's SCTE journal right now. So thank you, Business Bambi, for reading that. Ron and I and our co-authors really enjoyed writing that paper. We had a great time doing that. So.
And there will be a test.
Yes.
Just kidding.
Test at the end.
All right. Now let's continue our look at visual carriers. And I know that most cable operators have replaced their analog TV channels with digital signals, but there's still some analog TV channels out there. So let's consider a spectrum analyzer view on the left side of this slide here of a CW carrier. So this is the frequency domain. We see amplitude in the vertical axis and frequency in the horizontal axis. Guess what that equals? If we hook an oscilloscope up to that same signal source, we get the time domain representation of the same thing. And this is amplitude versus time, as you would expect on an oscilloscope, and that's a sine wave on the right. Now you look at that, you say, I don't see any individual cycles. If you adjust the time per division control on the oscilloscope, it'll spread it out, and then you can see the individual cycles of that sine wave. But that's exactly what we're seeing. So we're seeing the a CW carrier on a spectrum analyzer on the left in the frequency domain view, and we're seeing the same signal in the time domain on the right. They're the same signal. They're just different ways to look at them.
So Ron, this is such a good slide to help people visualize, and I struggled for a long time to understand the difference between the frequency domain and the time domain. This slide, I think, just really spells it out so that people can understand. The image on the left is the frequency domain, and that's your, as you say, your CW carrier, and it has a center frequency of 199.25 megahertz, just shy of 200 megahertz, where that CW is. And then what you're showing on the right is just a really high frequency representation of a sinusoidal wave that has a frequency of roughly 200 megahertz. So a beautiful slide, Ron. Beautiful.
Yeah, you tweak the time per division control on the oscilloscope, and you can see the individual cycles of that sine wave. All right, so now let's look what happens when we apply modulation. So in this case, we're looking at the frequency domain on the left, spectrum analyzer display of an analog TV channel. We can see the visual carrier and the color subcarrier. Now for this display, I couldn't disable the audio carrier, so I just deleted it on the screen just to show you what it looks like. So that's the frequency domain view of a modulated NTSC visual carrier. And here we're assuming no audio carrier. And there it is in the time domain. Same signal, just a different way to look at it. So the right side is the time domain on an oscilloscope, where the vertical axis is amplitude, horizontal axis is time. On the left display, you see the frequency domain, which is amplitude on the vertical axis, and the horizontal axis is frequency. All right, what about all those single carrier QAM signals we have on our cable network? Things are a little bit different there than they are with analog TV channels. We're still measuring power and still measuring signal level in dBmV, but what is that we're measuring here with a QAM signal? Well, remember, when we're talking about an analog visual carrier, we're measuring its peak envelope power. And in the instrument signal level meter actually expresses it in dBmV, but we are measuring the peak envelope power. However, when we're measuring the amplitude of a QAM signal, and this is also true of an OFDM signal, but when we measure the amplitude of a single carrier QAM signal, we're measuring the entire QAM signal's average power. We are not measuring its PEP. And this measure of average power of a QAM signal is called digital channel power or digital signal power. Now, most modern signal level meters and those that have been made in the last, 15 plus years, QAM analyzers, some spectrum analyzers, and other test equipment, in order to measure the average power or state the average power of that QAM haystack, actually perform a signal level measurement at several points across the bandwidth of that haystack. And let's say it's 6 megahertz wide. So depending on the instrument, it'll measure a slice of that channel signal level in several places across the haystack. It integrates the results, and then that gives you the average power of the entire haystack. And the way that's done is it typically will provide you with comparable results to what you'd get if you used a laboratory grade thermocouple power meter. Now, most of us don't have a thermocouple power meter to measure it, but those measure the entire signal too, but you have to make sure you're only measuring one signal at a time with a thermocouple power meter. But the signal level meters measure little pieces of it and then kind of glue all that information together to give you the average power of the entire QAM haystack. So there's a display you've probably all seen at one time or another. That is a single carrier QAM signal in the frequency domain, as you'd see on a spectrum analyzer. So that's amplitude versus frequency. That's a 6 megahertz wide QAM haystack. In this case, it happens to be 64 QAM, but 256 QAM is nearly identical. You really have a tough time differentiating between the two on a spectrum analyzer. If you look at the skirts on the two and overlay them very carefully, you might see a slight difference, but by and large, the naked eye, you're not going to see that difference. Time domain. Have you ever connected the output of a QAM modulator to an oscilloscope?
Yeah, I've never done that before, Ron. I think we even talked about that before. It's, everything we do in DOCSIS and cable, we pretty much do in the frequency domain. We typically don't look at these signals in the time domain. So I was really excited when you put this slide up to show us what a single carrier QAM looks like on an oscilloscope. So tell us about this.
This is a fun one. I connected it. It was a digital oscilloscope I had access to, and I just plugged it into the output of a QAM modulator. It's a 64 QAM signal. I took a bunch of different pictures with different time per division settings, and one of them I've got. I don't show it here. You can actually see where the phase shifts, because with QAM, quadrature amplitude modulation, you're actually varying the instantaneous phase and amplitude of the signal to represent different symbols or groups of ones and zeros. So you can see here, you can see that this burst on the left, if you will, represents a symbol. So it's got a certain amplitude and phase. And then down here, the phase shifts and the amplitude gets a whole lot bigger. So what would that tell you? If you're looking at it on a data constellation, the one that's got the real high peak-to-peak amplitude is a symbol point in the constellation is out near one of the corners of the constellation display. And then you get another phase shift, and then the amplitude drops, and then you another phase shift, and the amplitude goes up. But you notice the amplitude is varying all over the place each time it changes, and there can be subtle phase shifts or big phase shifts that represent the location in a constellation display where that is. And what we're measuring is the average power of all this to get the signal level, or the average power of this full haystack. But this is a time domain view of a 64 QAM signal, and it really looks a lot different than we're used to seeing, and it is pretty cool. So let's wrap up here. What is signal level? Well, it's the amplitude of a signal, but in the world of RF, it's the power of that RF signal. That's what signal level is. Signal level in cable networks is expressed in dBmV, not dB. Remember when we talked about that in our last session on the fundamentals of the decibel?
And so important.
You can't use the dB by itself to express signal level. That is incorrect. You can express loss and gain and attenuation and return loss and structural return loss and isolation and carrier to noise ratio and so on in dB. But signal level must be expressed in dBmV, or if you're in Europe, dB microvolt. And remember that dBmV gives us peak envelope power, but it's a unit of power expressed in terms of voltage, and hence that MV at the end of dB. So when we talk about measuring the signal level of an analog TV channel's visual carrier, we're measuring its peak envelope power. With an SC-QAM signal, we're not measuring PEP. It's still dBmV, but it's expressing power in terms of voltage. Here we're measuring its average power, and we call that digital channel power or digital signal power. Now, a moment ago, I said dBmV is peak envelope power, but in the case of the QAM signal, no, we're just talking about average power. Now, in the case of a downstream OFDM signal, the power that we measure is average power, but it's the power per 6 megahertz. And most meters that measure an OFDM signal measure the power per 6 megahertz chunk of that signal. You can measure the total power of that, but for most people, the interest is in the power per 6 megahertz, and that's actually defined in DOCSIS to be measured that way. And that really gives us an equivalent value to our SC-QAM signals.
And this 1.6 megahertz reference that only came about as part of the DOCSIS 3.1 specification, correct?
Yes.
That's not something we talk about in previous versions of DOCSIS.
That's correct. And typically, at least in the upstream with OFDMA, the power is the power per 1.6 megahertz. But and that's actually in the spec. And then people complained and said, but we're used to measuring the total channel power. What is it in 6.4 megahertz? So some people prefer to normalize the 1.6 megahertz power to 6.4 megahertz. You need to add 6 dB to the 1.6 megahertz value to give you the value for 6.4 megahertz. And I think most modems and CMTSs now have an option for you to get the reported power at the input to the CMTS, or the cable modem transmit power in the upstream in the channel power. That is the 6.4 megahertz power rather than 1.6.
Yeah, so we had an episode like 2 episodes ago. I'll try to remember to put it up, link to that. But Larry Wilcott talked about some of the challenges with measuring like cable modem transmit power, particularly when we're measuring it with respect to a 1.6 megahertz reference. So we kind of got into a little bit of those challenges and all the work that Larry's doing on cable modem transmit headroom. So
yes, and that's all a good point
up there.
Yeah, that's a good one. All right, so I'll ask the question. For those of you who are watching this session today, first of all, thank you. But are you a math fan, a cable mathematics fan? And some people will go, no, I'm not interested in math. I don't like math. But if you are a fan of mathematics and cable, or would like to learn more about it, there is a document. It's an operational practice available on SCTE's standards download page. And it is called SCTE 270 2021 R1. The R1 means it was revised, and we made some minor editorial tweaks to it to fix some typos and a few other minor things. So that R1 is the latest version. There's the URL where you can get it. You can go to SCTE's website, scte.org, and you can navigate to the standards download page. And when you get to the standards download page, you just scroll down through the list of standards and operational practices and other documents till you come to SCTE 270, and then download that. It's a big document. When NOS Working Group 1, which is a working group I chair, originally decided to create a math document, we thought, this might be 50 pages of formulas and examples of how to use them, maybe 100 pages. Well, when it was all said and done, it came in at 425 pages. There are mathematical formulas and examples of how to use them for just about every formula or every situation you can think of in cable. And the appendices have some essays that do a deep dive on some of the topics. But most everything that you could need is covered in this document. And it's a great reference to have, even if you're not going to read it all. I think most people would use it as a reference to say, what's the formula for carrier to noise ratio? By the way, our next session is going to be on carrier to noise ratio. So we'll take the concept of the decibel a little bit further. So we've talked about the fundamentals of the decibel so far. We talked about signal level and using dBmV to measure it. So up next is carrier to noise ratio. So that should be a fun one. So
that SCTE 270 document is a fantastic document. I'm glad you recommended that. You can also just search on that document, and it'll come up in a Google search. So local.
Make sure you get the R1 version. That's the latest version.
Yeah. And Local Trees, thank you so much, Local Trees. I know you're a big supporter of our channel. He says thank you for coming on, Ron. So definitely, thank you so much, Ron. This was great content that you provided, and it was a follow-up to our What is a dB, which I think was a great episode, very well watched. I'll try to remember to put a link to that also up in the top so everyone can see that. Anything coming up or anything you want to promote, Ron, before we wrap up?
I can't think of anything right offhand, Brady. I think we've covered it nicely. Hopefully the presentation helped to clarify the concept of signal level. It's one of those concepts that can be a little bit difficult to understand, and understand, of course, that it has its foundations in the decibel, which we've talked about in the previous session, and also understand that you can't express signal level in just dB. That's meaningless. And yes, we all do it or have all done it at one time or another. I've got 3 dB at the input to the cable modem. That is inaccurate. It's 3 dBmV. Use the 3 dBmV and understand what it is that we're stating when we talk about signal level. Peak envelope power for an analog TV channel's visual carrier, average power for a QAM signal or an OFDM signal or an OFDMA signal, and understand that the dBmV or dB microvolt, if you happen to be in Europe, is a much easier way to express signal levels, because if you had to state it in power in units of watt or microwatt or nanowatt or volts or microvolts or millivolts, you'd be pulling your hair out trying to do that. So hopefully this simplifies things. I remember one of the questions we had in the session on decibels was, well, how does all this apply, decibels, to things like carrier to noise ratio and carrier to distortions? And those sessions are coming up.
Yes.
As I noted, the next one's about carrier to noise ratio and what it's all about, what it is. So that'll be a fun one. And I think that's it.
All right. Outstanding, Ron. Thank you so much for all the information. It's been just such a great piece of information. And so that's a wrap on today's episode of this series on RF and cable basics. This was our second episode. As Ron said, we're going to have another one. I hope you found this discussion on signal levels as interesting and informative as I did. I learned something from Ron pretty much every time I get the opportunity to talk to Ron. He has such great experience. So a big thanks to Ron for joining us today and sharing his expertise with us. If you like the show and enjoyed the show, please smash that like button and also subscribe so that Ron comes back and drops more information and knowledge on us. And folks, the learning doesn't stop here at the Volpe firm. I'm excited to announce I'll be attending the Light Readings Cable Next Gen Technologies and Strategies event on March 14th and 15th in Denver, Colorado. So if you can, please join me there. I'd love to see all of our listeners. I'll also be attending Cable Lab's P&M face-to-face meeting during the last week of March. Ron, I think you'll be attending that as well.
I'm
So
planning to.
I'll see you there. And so anyone who's involved in Cable Labs P&M working group, hope to see you also at the end of March. And don't worry, we will be back on March 24th with another episode. I think it's episode 90 with John Downey and I to discuss DOCSIS 4.0. So we'll be coming back from the NGN episode with light reading on basically what the next things that we've learned, what's happening with DOCSIS 4.0. So mark your calendars and make sure to tune in to that one. Until then, thanks so much for watching. Remember, stay curious and keep learning. So long, everyone. So long, Ron. Thanks so much.